Okay, so in this video I'm going to do a couple things. First of all, I'm going to recap how we derive the rate laws. Secondly, we're going to figure out what the rate constant K is for these situations. And one of the more important things is that I want to talk about the units for K, all right? Because it's a little bit different for uh, versus a lot of things, because with a lot of properties, the units are always the same. For example, if we said speed, it might be something like miles per hour or feet per second. But so it fits always a common format of some unit of distance divided by some unit of time. The thing with K is that the units can be different depending on whether you're talking about a first order or second order type of reaction. All right, so just recapping, and I know that we did this first one in class. All right, if we wanted to figure out what the rate law is for this, remember what we want to do is we want to look at a situation where one of the reactant concentrations is held constant and we double the other. All right, so in this first situation between experiment 1 and experiment 2, we can see what the original observed rates of the reaction were to be. We can see that when A is constant and you double B, you get a doubling of the rate. All right, that would mean that with respect to B, it is first order. All right, and that's why I left that blank right there. You could put an exponent 1, but we know that in math you don't generally put an exponent of 1. All right, so what about for A? All right, in the situation between the first experiment and the third experiment, we can see that B is held constant, but that we're doubling A, all right? And we can see when that happens, that results in a quadrupling of the rate, all right? And so that would mean that it is second order with respect to A. Overall, this reaction would be considered third order because you add the exponents and that's what you would get, all right? So, so now that we have the rate law for this reaction, we can go and solve for K, all right? So just taking this expression right here, and we could have picked any one of these experiments to do this with. It should give you the same unit measurement for K regardless of which of these experiments. I'm just going to pick the first one right here. Okay, so what is the rate? The rate is what we have right here, 2.0 times 10 to the minus 6th molar per second. All right, and we write that down, and equals K, and then we're just going to plug in for our different concentrations of molarity. All right, so we would get this expression right here, and what I'm going to do from here on out is just kind of focus on how we get not only the number but the units as well. All right, so in terms of the numerical part of the solution, all right, we would square, first of all, we're going to be isolating this variable right here. So if we square 0.2, that would be 0.04. This part right here would be 0.01. And if we move those over to the other side, you can see that the numerical part would be this right here. If we solve for that, we get 5 times 10 to the minus 4th. All right, notice that I said 5 times 10 to the minus 4th because if we apply our significant figure rules, you'll notice that each of these values right here have only one significant figure in them. Therefore, our answer should only have one significant figure. That's why it's not 5.0 times 10 to the minus 4th. All right. The harder part comes in figuring out the units. All right. So remember that in determination of your units, you do the same mathematical operations to your units as you do to the numbers. All right. For example, when you calculate the area of a square, you would have a centimeter times a centimeter, so the units of your answer are centimeters squared. All right, so let's take a look at the units that we have here. All right, we have, this is molar per second. All right, this is molar and this is molar, but notice that this part right here would make a molar squared, and this would be plain old molar right here. And if you did that, you would notice that like a molar squared times a molar would make a molar cubed. All right, so taking a look at this, we have a mole. So if we move that molar cubed from this side to the denominator over on the other side, we would have a molar per second divided by a molar cubed. All right, and the way to clean up these types of complex fractions is to do that operation called keep, change, flip. All right, we're going to keep the numerator. All right, that's why we have this. We're going to change it to multiply, and we're going to flip the denominator. All right, so the flip of molar cubed is 1 over a molar cubed. And when you do that, one of your molars on the top will cancel with one of your molars in the bottom, and you end up getting this unit right here. All right, notice that these are in the denominator, and so that when I write the unit, a common way to do it is just to say this thing to the negative of what its exponent is, and this thing to the negative of what its exponent is. So the way I would say this is 5 times 10 to the negative fourth per second per molar squared. Okay, moving on. Taking a look at this data right here. Again, if we look at what happens when you double b, it looks like it doubles the rate. That's why it's first order there. If we double a, we can see at a constant b, we can see that that also, going from here to here, doubles the rate. All right, so we would have, it would be first order with respect to each of the reactants. All right, and remember when we write the rate law, we won't put in the ones. All right, so in order to determine the actual rate constant here, we are going to start by plugging in our values. And again, we could pick any one of these that we wanted to do. All right, so I've just chosen the first one. And again, we do the same thing where we're going to calculate the number part separate from the units part. All right, so the numbers part I'm assuming you guys can do, but let's take a look at the units. This is a molar per second, but we've got a molar and a molar over here. Multiplying these by each other, that would be a molar squared. And when we're going to eventually take that to the other side over here. So again, we're going to have this part right here. That's the numerator right here. And then you've got the molars, and I just wrote it as a molar times a molar instead of molar squared. Again, keep, change, flip. Keep the numerator. Represent the flip of the denominator. That's the reciprocal of that. One of your molars cancels out, and you end up getting 1 over top of a molar per second. All right, so this is the numerical part. We take this and we divide it by the numbers over here. And so our answer, again, instead of writing the unit as a 1 over a molar per second, you just write them as the negative exponents of that. All right, so the last one, we are just going to take a look. Okay, what happens if we double b? We can see that if you double b, it actually quadruples the rate, the initial rate. All right, notice it doesn't. You have to pay attention to the scientific notation right here. All right, if you're not paying attention over here, it looks like the number actually goes down. But remember, this is times 10 to the minus fifth times 10 to the, this is to the negative sixth, and so this is actually a much 4 times greater than this number right here. All right, so that means that it is second order with respect to b, because it doubling this quadruples this. All right, but what happens with respect to a? All right, well, if we keep b constant, which is what happens between the first and the third experiment, and we double a, what happens to the rate? We get absolutely no change in the rate. That means that it's 0 order with respect to a. All right, and so when you write the rate constant, anything to the 0 order becomes 1. All right, so therefore we don't write that in the rate equation, and that's why we only see b to the second power. And again, you can kind of go through this. You know, there's part of this where I'm calculating the numerical part. There's part of it where I'm figuring out what the units would be. Notice that I'm just going to kind of recap the units part. Notice that in both of these right here, we have different looking rate equations. All right, This one right here is first order with respect to A, first order with respect to B. This one right here is second order with respect to B. All right, but overall, the reaction here is overall second order. The overall reaction here is second order. Therefore, your units for K end up being the same. All right, so let's compare that to this reaction here, where the overall reaction was third order, which resulted from a second order reactant and a first order reactant. And notice that the units for K and the overall third order reaction is different from the units from K in an overall second order. All right. Notice we haven't done an example of a reaction that's overall first order, but you can get the units just by doing the same type of thing, where you plug in your units and you just see what units are left after you do the math. All right.